Our guest today is Alexandre Zimmers, who is a scientist at ESPCI in Paris, which stands for École Supérieure de la Physique et de Chimie Industrielles. He's also a professor at the Sorbonne University. So welcome, Alexandre.
Hi, thanks for having me.
So one of the things we like to ask researchers in this field is, why are people so excited about all things quantum right now?
Well, hi, Erica. Thanks for inviting me. Well, I think in condensed matter physics in general, people have been interested in a fundamental on a fundamental level on basically the possibility of discovering new states of matter, new orders, and on a practical side, this could lead to creating new detectors, sensors for everyday life. And I'll try to. I'm here in a special location. I'll try to give you an example of how seemingly small this initial discovery basically contributed greatly to the development of nanotechnology over the 20th century. And so this is the discovery of piezoelectricity in the mid 19th century. The common material that's piezoelectric is quartz crystal. So I brought actually a prop here to show you what you've probably seen, and you can see this in crystal stores. So I don't know if it's going to focus properly here, but so
for those of us who have our own crystal collections, have quartz.
All right. So this one is pretty neat. It has the property of the following property. This piezoelectric property is that if you take it and you compress it, so you push on it, you actually, because of the crystal symmetry and the arrangement of the atoms inside, you actually have a voltage that builds up on the sides of the quartz crystal, and that people have been played around quite a bit for a long time in the 19th century there. And in 1880, Pierre Curie and his brother actually discovered something. The inverse was also possible, meaning that if you apply a voltage on it, you actually take a battery and you put two electrodes and you apply a voltage on it. This quartz crystal will expand, change shapes a little bit. You won't see it by eye, but it's there. And so it's this funny property that seems modest in the beginning, and even Pierre Curie himself mentioned that it was modest. Actually has endless applications over the last 100 years. So Paul Langevin in this laboratory here where I'm sitting, 30 years later, so in 1917, actually used this fact that the crystal changes shape. And what he did is something interesting. He actually applied a voltage, but he actually applied a voltage that changes way. So he did plus minus and then switched it around and then minus plus. And he inverted this DC voltage rapidly. And what happens in this crystal in that case is that it expands and contracts rapidly. And what he did with that is that he immersed this quartz crystal into water and made the water vibrate, and that what's created the ultrasounds for the first time. So in this room, about 100 years ago, in a sink I'll just turn the camera to show you what I'm seeing here. The sink that you see right in front of you is actually the place, the historical place where Langevin, Paul Langevin, in 1917 immersed this quartz crystal in this sink for the first time and saw the water vibrating. Now he did it to create sonars to detect, to detect boats, submarines. This was actually, there was a military application. It can be used for schools of fish, to detect schools of fish and whatnot in the ocean. And in everyday life, these, what we call sonic transducers, are used for in medical applications for sonograms, to clean your jewelry in sonic baths, for inkjet printers, and even something that's even more fun. It's the birthday cards, the singing birthday cards. When you open it, it makes a sound. That's a little piezoelectric. That's actually a speaker that makes that sound.
So that's very cool. Actually, my daughter is the biggest fan in the world of singing birthday cards. So when she's got one in her possession, that thing is played. Making this video, I
actually realized that there are birthday cards you can tape the message yourself. Now so I'm actually thanks to your video, I'm actually going to do that next time. So that's a good that's a good thing. So the amazing thing with this material is that it doesn't stop here. if you take this material and you apply a voltage on it, you can actually make the most precise pen on Earth. So what I mean by this is that if you apply a voltage and it expands, you can actually bring this down to a surface and approach this quartz to a very, very, very precise, to a very close height without crashing in it. And this is what's used in modern equipment called STM. And one of the state-of-the-art STMs in the world is actually right behind me, where this is a scanning tunneling microscope that brings a metallic tip. So you have to imagine that connected to the quartz crystal, you have a little metallic tip that you glue on it, and you bring the whole thing down close to the surface. And thanks to this setup, you can actually bring down this pen and measure the surface of a material atom by atom on an atomic scale. And that's an incredible application that one could not imagine in the beginning 100 years ago. And so in this room, you really have from the beginning of the sink where Langevin plunged his quartz material and created ultrasound, to the really high-end experiment that's behind me, the STM. And just to finish on how things sometimes are amazing, you discover this property and the consequences that you can't imagine in the beginning actually happen over time. This quartz material, if you put something on it, it creates a voltage, so you can create a little scale. That scale is what you use in your kitchen scale that you can buy. You can actually also take a quartz material and put it as a tuning fork. So you create out of this little material here, you create a little U, and you make it vibrate. And when you make it vibrate, you can actually measure the number of times it vibrates over a second. And you can measure the second precisely, the time. So it turns out with this material, this property, this piezoelectric property in the beginning, you really have the most, not the most precise, but a very precise and cheap way of measuring mass, time, and distance over the last 100 years. And so I guess by this example, I just wanted to say that you have the possibility of you hope that by looking at quantum materials nowadays, superconductors, graphene, topological materials, one can hope that by discovering a new phase, you can really hope to find some game changer that the same way the piezoelectric changed a lot of things.
That's great. So tell us just real quick, this STM that's very precise in measuring distance, how small of a distance can it measure?
Well, it comes down to you actually have to tell it the STM you bring down. So you bring a metallic tip connected to this crystal. Okay, so I don't have this metallic tip connected to it, but you have to imagine that there's a little wire, and you have to tell it when to stop. So you can go down very precisely, but you still need to know when to stop. And the STM has a particular fact that it's using the fact that when you are close enough, you actually have a current that's passing from the tip to the sample in vacuum. That's called a tunnel current, and it's over a few nanometers. You can actually scan the surface of your material with this tip following every bump and every surface, every atom of your material.
Okay, so it's a way that we can actually go in and measure, in a way, look at atom by atom by atom inside of a material and find out what's going on.
Yeah, absolutely. Yeah. So at the end, you really have an image of what you have in your sample, and you know, when you talk about something becoming metallic or something becoming insulating or semiconductor, well, now you really have a way of seeing if every part of your material is in that state.
Okay, so one of the other things we're curious about in these discussions with scientists who work on things that are quantum, you work on quantum materials, for example. What originally got you interested in doing science?
Well, I guess probably like a lot of kids taking things apart and not putting back together, of course. So that was my first thing, seeing how things work inside. But you know, then to become a bit more concrete, going to the science museum. Really, in Paris, we have a great science museum called the Palais de la Découverte, the Palace of Discovery. It's at the bottom of the Champs-Élysées. It's really in the center of Paris. and it shows, it treats chemistry, biology, geology, physics. And the particular thing about this museum is that it actually has science mediators that explain things to the public over 30 minutes exposés or an hour. And it really shows, it helps you go through the difficult concepts by a science show. So I would say that if I had, if I had an advice to, if you can bring children to science museums, that really can create a spark. If you see the superconducting levitation as a kid, that really is something you remember easily. And if you don't, if the science museum is not really around you, there's nowadays that what we're doing here, the YouTube video is something really useful that you can follow. Certain YouTube channels are great to do a little experiments at home. You can order things online. There's actually since this is a coffee house, I actually brought my favorite mug, and this is the one I use every day. So this is actually from a science store in the Midwest called American Science in Surplus, where you get into the store and you can basically buy everything needed to play around and do these little science experiments. And there's one in Chicago and Milwaukee. So I'm sure around you somehow a science store, a science museum, or really just YouTube channels is a great start for kids to get into science.
Very nice, very nice. This is my first time hearing about that store, and given that I live maybe 2 hours south of one, I think I'll be making a pilgrimage to this store.
It's hard to go out without buying a full basket of
no,
things, for sure.
I have a list of magnets that are hard to procure, so I think that's probably a good place to get it.
They have a whole section of magnets.
Fantastic. I'll never leave the store. Great. Well, okay, so, all right, so you're currently a researcher, currently a scientist, and of all the great things that are going on in your lab right now, what's the thing you're most excited about right now?
Well, there's a lot of things, of course, going around. In my lab is located at the ESPCI, so the school actually, we do research in physics, chemistry, and biology, about the same they are balanced out, 1/3, 1/3, 1/3. Of course, in my field, my direct field of research, I'm really excited about these local probes, what I'm showing you behind. It's it's probes that you can use your simple microscope to look at things over a micron, but you can look at you can use STMs and other local probes to look at atomic resolution, a few nanometers wide a material, and see what's going on at that scale. And you can really see what makes a metal become a metal, or a superconductor be a superconductor, or a semiconductor being a semiconductor. So that's really great visually to have an image. And you can also see something very interesting is that if you have materials that have a phase change, like you can, the most known is water going from liquid to ice. Well, in materials, the same way, you have materials that go from one phase to another. You can go from a metal to an insulator. You can go from a superconductor to an insulator. You actually can see locally how this phase changes. So of course there are theories, and you can compare these images to the theories that have been developed. So that's really something that's been very successful over the last decades. Nowadays there's actually a family of materials that when you pass that transition going from phase A to phase B, well, there's a lot of mixing that happens. It doesn't happen homogeneously, and it becomes really a mix between the two phases over a large temperature range. And understanding that really helps you out understanding why, what makes that material so looking at those images helps you understand what the physics underlying physics. And it really also gives you the opportunity of the following opportunity. If you put an external perturbation on these materials, such as an electrical field, you actually apply a voltage across them, or you apply a magnetic field, you put it next to a magnet, or you apply pressure, you compress it or you expand it, you can hope that you favor one of the phases compared to the other. You favor phase A compared to phase B. And this, in that case, becomes something called some soft electronic matter. And that is hoped to be the key ingredient to make great detectors and great sensors for everyday life. But these materials that have this mixed phase, there have been very active research going on to try to see if they can create and mimic artificial neurons and synapses. So in a biological brain, the synapse part of your brain, the synapses transmit the information from neuron to neuron and keep the memory of past signals by connecting neurons more or less in a good way. Neurons, on the other hand, they integrate a lot of signals coming from other neurons before them. They integrate the whole signal and decide to spike or not with a threshold mechanism to pass on the information for the neurons after it. And so these two key ingredients in the brain are the spiking and the memory from the neuron and the synapse. That can be artificially created by a computer program. Over the last years, that's been done very successfully, but except it takes a lot of computer power, a lot of computer volume, because you need super calculators. And what's hoped is that these materials that actually have this phase separation, A and B, are susceptible enough that they could actually be good candidates to create these artificial neurons and synapses. It's been shown that you can actually put them in the right configuration and they will spike. They will create the spikes that you know from neurons. And they will also keep memory from past signals. And so they really have the two key ingredients to create a artificial neuromorphic circuit that could be used in the future for artificial intelligence.
Great. Well, thanks so much. That's all very interesting stuff, and we're out of time. So I'll go ahead and just thank you for joining us.
Thanks for having me.